Okay, good morning. So let us start the next lesson. Of course, this would be very simple. Mainly, I want to rely on your intuition about that. So we want to extend two-dimensional coordinate system to a three-dimensional coordinate system. I don't think it should be hard, but drawing those pictures would be a little bit problematic here. So I don't know if this is a good idea or not. I'm assuming that x-axis is on the whiteboard, z-axis is also on the whiteboard, but I'm assuming that y-axis is actually going behind the board. So somehow you have something like this, yes? So here, in this way that I am thinking, this is the x-axis and this is the z-axis. And this is supposed to be the y-axis, yes? This is what is, I don't know, is that clear or not? So this axis is perpendicular to that one, this one is also perpendicular to that one, and then you also have this one perpendicular to this one. So anyway, then any point in space can be addressed by three numbers this time, yes? So before that you had a point, for example, A, you had only two coordinates, but here now, if I want to address a point in a space, okay, then I have to give you three numbers, x, y, and z, okay? The x coordinate, the y coordinate, and the z coordinate. And of course, these numbers could be positive, 0, and negative, depending which point you are referring to. I think it would be easier for us to understand it in that way. So if I have these three axes here, and by the way, what is very important, we always work with a right-handed coordinate system. The meaning of right-handed coordinate system is that you can have two axes, x and y, and then you can have two different directions for choosing the positive y, z. Yes, so for example, if this is the x-axis, and this is the y-axis. Okay, this is the positive part of the x-axis, this is the positive part of the y-axis. I could choose to have z in this direction, or I can choose z in this direction. Okay, we always choose z in this direction. This is called a right-handed coordinate system. It means that if I bend my fingers in a way that takes the x-axis to the y-axis, my right hand, then my thumb should point in the positive direction of z. Yes? This is right-handed coordinate system. I can have it in that direction. Then of course this is left-handed coordinate system, because if I take my right hand again and do the same thing, my thumb will point upwards, but I am choosing z in the other direction. So this is a crucial. So remember that always we choose x and y and z in a way that we are always working with a right-handed coordinate system. Yes, that is what we choose. And then I think you probably know, if I have a point here, then the distance of that point to the x-axis, so this is a little bit different. So if I have two coordinates, two axes, then if I take this point, and I draw a perpendicular line to the x-axis, then this distance is the x-coordinate of my point, of course considering on which direction it is, yes? And then this distance is the y-coordinate. But here, I can also do the same thing, but of course drawing the pictures are hard. I can draw a line from here perpendicular to the x-axis, but you need to visualize it in a space, something like that. So if I draw that one, then this can play the role of the x-coordinate. Is that understandable? So you have a point in a space, you take that point and just draw a line perpendicular to that one. But of course, being perpendicular in a space would be a little bit different. For example, this is the x-axis, my point is somewhere here. I take this and just draw this perpendicular line to here. Whenever it connects, then that point from the origin, which you can call it O again, playing the role of x. But of course, in this case, for this point, you see that x is positive. It might happen that this point is behind this plane, And then, of course, if you do the same thing, it will end up on the negative part of the x-axis, and the x-coordinate would be negative. But that is also, so if I want to do the same thing for the y-axis, so I don't know if this is a good way of doing it, but you understand what I mean. Then from here to here is the y, and if I do the same thing for this, yeah, probably that's probably not a good way, because I am working it. Oops, this is very bad. I have to change this. And if you do it, I don't know, I cannot draw artistic pictures, but hopefully it is understandable for every one of you. So that point A has these coordinates. So from here to here is x, from here to there is y, and from here to here is z. Yes. Okay. For example, can you tell me what are the coordinates of this point? If the coordinates of this point are x, y, and z. So I don't know. Let me call it, for example, A1. What are the coordinates of this point?
X, 0, 0.
X, yeah, exactly. The x coordinate of this point is exactly the x coordinate of that one, but the y and z coordinates are 0. Yes, it's very simple. So here, what are the points? So if I have A2, I will have 0, y, and 0. And if I am here, I will have 0, 0, and z. So that they are clear. Okay, one thing that's important, can you tell me, if I project it here, I mean that if I find the shadow of this, if the sun is actually exactly up there, and then I am finding the shadow of this becomes a point B. Okay, can you tell me what are the coordinates of this point now?
X, Y, 0.
Yes, it is x, y, and 0. But that is important to realize that x, y coordinate of this is exactly x, y coordinate of that point. But of course, it is lying on the ground, so the z component, which is called the height usually, is 0. Yes? And then important thing is that if I connect this one to that one, this also becomes perpendicular to that. So this is important to realize. So if I want to reach to this point A1, I can do it in two different ways. I can take my ruler and find this perpendicular line to this axis directly, or I can project it onto the plane and from the plane draw a perpendicular line. Yes, they will intersect exactly at the same point. Okay? But of course, if you want to prove them, you need to know some axioms of Euclidean geometry. But I think intuitively all of us agree that this would be the case. Yes? So you see, by the way, in plane geometry, if I draw a line, assume that I want to be on the plane, and I give you a point, and I ask you to draw a line that is passing through this point and perpendicular to this line. How many lines you can draw if you want to be on the plane? Exactly one. Yes? But it is different when you go to space. Yes? If I have this is my line, if this is my line, of course all these lines in space are perpendicular to this line. But if I want to be on the plane, then there is one unique line. And so that is not strange. You see here, this line is perpendicular to the x-axis, and this line is also perpendicular to the x-axis. But they are perpendicular to the x-axis in different planes. This one lies on the ground, so it is perpendicular to the x-axis, but in this plane. And this one is perpendicular to the same line at the same point, but in a different plane. Yeah, so this can happen. But this picture, it's always good to have in mind. And I can do the same thing for the other parts. So these are intuitively very, very clear, so let us not spend so many time on it. And then, do you remember this? We call it x-axis and y-axis. Of course, here we have x-axis, y-axis, and z-axis. But here we also have coordinates. So these are called axes, but we also have coordinate planes here. So this plane on the ground usually is referred to x-o-y plane. Or sometimes they write it just xy plane. So it means the plane consisting of these two axes. Yes? And how many planes we have? We have three of them. X, O, Y, and then I don't know, X, O, Z, and then we also have Y, O, Z. Yes. So these are called coordinate planes. That's good to know these names. Okay, more or less everything we had done for two-dimensional geometry, we can also do it in three-dimensional geometry. Yes. For example, you remember we had a distance formula in 2 dimensions. We can also have a distance formula in 3 dimensions. Okay, let me make sure that I am following everything that I'm supposed to say. Yes, good. So, what do you think would be that formula in a space? Do you remember what was the formula in the plane? Of course, you need to prove them, but they are not hard, so I want to leave them for you. So you need to convince yourself what I write as a formula here is actually correct. Except some of them that I will repeat. So if you have a point here in plane called with coordinates x1 and y1, and if I have another point here with coordinates x2 and y2, we know that how we should find the distance, yes? What was the distance formula? It was the square root of the difference of x coordinates, yes, plus the difference of y coordinates. Of course, each one of them squared. So that would be the distance formula. But I think it is easy to predict what will happen for 3 dimensions, yes? So then I will have one more square because of z coordinates. Of course, you need to convince yourself. Again, the idea is using, so here the idea was using one Pythagoras theorem, 1 times Pythagoras theorem. So you just draw this and that. And then you measure this distance, which is this 1 to power 2, this distance, which is this 1 to power 2. So you use Pythagoras theorem once, and then you find that. But if you want to do it in a space, it seems that you want to find the diagonal of a rectangular cube. Yes, so can you imagine that? Yeah. So in that case, I need to use the Pythagoras theorem 2 times. Yes. So I don't know, I use the Pythagoras theorem to find the diagonal, then I take this diagonal with the height to find the other diagonal. So I need to use it two times, and it would be very easy to convince yourself that in 3 dimensions the distance formula will take this one. Will take this form. Yes? So that is the distance formula for 3 dimensions. So for example, let me ask you, we can solve a lot of problems, actually simple problems. I don't want to spend so much time on it. So let me write this, at least this session. Yeah, so there's very simple problems I skip. For example, I can give you 3 points with 3 coordinates, and I can ask you, show that the triangle is isosceles, for example. Or I don't know, show that the triangle is a right angle. So you find the lengths and compare them. So that's very easy. So let me give you a little, it's also easy, but let me just write it here for you, at least to have one example here. Consider the points A with coordinates 3, 2, minus 2, and B minus 3, 1, and N. What is the minimum distance from B to A? Of course, A, the point A, the coordinates are given, so A is a fixed point, but B is not a fixed point because its third coordinate is a parameter that can change. Okay, before doing this calculation, what is the locus of point B? Now, can you imagine it in a space? Is the question clear? So it means that if you start changing M, B start moving, yes? And so then what is the shape that is generated by B when M is changing?
A line?
A line, more if you want to express it more.
Parallel to z.
Parallel to z-axis, yes, because you see that the x and y coordinates are fixed. So if I have, I don't know, if I have, for example, two axes, I have a point, of course, it's minus, so if this is x-axis, this is y-axis, so it is somewhere here and here, yes, minus 3. And then the z-coordinate is actually can vary, yes, that would be a line perpendicular to the ground, or as you said, parallel to the z-axis. And of course, A is a fixed point somewhere. So it means that this point is going up and down, and I have different distances from the fixed point. I want to see when it becomes minimum. Yes? And that is, I think, you should imagine without calculation, it should be possible. It is good to imagine because it will increase your imagination skills. So can you imagine what would be M if you understand this picture? So you know that A is somewhere, is a fixed point, and then you realize that B is going to grow up and down by changing M. Yes? And of course here I have this distance, here I have this distance, so it is clear intuitively that the minimum distance should occur here. But where is that case?
-2.
M should be -2. Yes? So it is easy to understand it without calculations. But if you want to do it using calculations, so I calculate the distance from A to B by the formula. So it becomes square root of the difference of x coordinates squared, which is not 6 to power 2. The difference of y coordinates squared is 1, and the difference of z coordinates becomes exactly m plus 2, as you will see. So this becomes 37 and plus n plus 2 squared. So that was from geometrical point of view, you were able to guess that m should be -2, and from algebraic point of view, you should also be able to argue that m should be -2. Why? Because you want to make AB as small as possible. Okay, AB has this formula. 37 is fixed, you are not able to do anything with 37. What you have in your hand is just changing m. And on the other hand, you know that m plus 2 to the power of 2 is non-negative, so I cannot make it negative if I want to make it smaller, so I have to make it minimum. But what is the minimum? The minimum of this is 0, so it means that if you ask about what is the minimum of AB, the answer is a square root of 37. When it occurs when I am choosing m equals to -2. So which one is wanted? The minimum value is wanted, so that is the minimum. Okay. So do you remember after the distance formula in two-dimensional case, we had a formula for finding the coordinates of the midpoint of a line segment? Yes? And that is exactly the same thing here. So do you remember? So if I had 2 points and I want to find the midpoint, this concept can be on the plane or it can be in the space. It doesn't matter. I can have 2 points in a space and I want to find the coordinates of the midpoint. So can you guess what is the answer? So let me write it here. So if A are coordinates x sub A, y sub A, and z sub A, by the way, that's also a standard way of writing x coordinate of A, y coordinate of A, z coordinate of A, and then I will have this x coordinate of B, y coordinate of B, and z coordinate of B. And then this point M is the midpoint, meaning that MA, the length of MA is equal to the length of MB, and I want to find the coordinates of the point M. So that is three-dimensional extension of that formula that you had in Math 1C. So what is the formula? Do you remember? Xm is what? XA plus XB divided by 2, and then I have YA plus YB divided by 2, and then I have Z of M is ZA plus ZB divided by 2. Yes? So these are the coordinates of the midpoint. So don't get confused, this is not half of the line segment. If I ask you what is the half of the line segment, of course you can calculate AB and divide it by 2, but I'm asking you about the position of the midpoint. So these are the coordinates. Okay, let us do some examples and exercises here. So I think I can skip very, very simple problems. Let me write one very simple one. At least we have some example. So example. Let A with coordinates 1, 2, 3, B 4 minus 2 minus 1, and C with coordinates 6, 2, and 3. Be the vertices of a triangle. Okay. Let me make it very simple first. Part 1, determine the length of the median AM. This is very simple. And 2, determine the coordinates of the centroid. Center of gravity, the concurrency point of medians. Okay, the first one is very simple. You can just sketch a rough picture for yourself. I don't know if this is true or false, but I don't really care. So, but here, this is just M. I want to convince myself how should I calculate the length of AM. So to calculate the length of AM, it means that I need to find the distance between these 2 points. And if I want to find the distance between 2 points according to the distance formula, I need to know the coordinates of A, which I do, and I need to know the coordinates of M, but I can find, yes? So it is easy. So let me just simplify it. M is what? 3 fractions. I add x of b to x of c and divide it by 2. It gives me x of n, and the same thing for y and z. So what is xb? It's 4. What is xc? It is 6 divided by 2. And then the y coordinates 2 plus minus 2 divided by 2. And then 3. Oh, sorry. Yeah, that's correct. 2 minus 2 plus 2, it doesn't matter. And minus 1 plus 3 divided by 2. 4 plus 6 divided by 2, minus 2 plus 2 divided by 2, minus 1 plus 3 divided by 2. So it means that M is 5, 0, and 1. This is M. And then I know the formula for the distance formula. So this becomes square root of, I need to take this one and that one. The difference between x coordinates is squared is 16. The difference between y coordinates is squared is 4. And the other one is also 4. This becomes 24. Yes. Square root of 24 length units. But the good question is number 2. How can I find the coordinates of the centroid? Any suggestions? Yes?
I have a hard time remembering. The centroid was the gravity point.
Yes,
Right.
which is the point of concurrency of the all medians.
Of the medians. Okay.
Yes. I don't know if you want to think, I can pause recording for some minutes. You don't need to calculate, just give me the motive, I don't know, just a strategy. How do you want to think about and solve the problem? Okay, any ideas? Yes?
It almost feels too easy. I mean, you can just do the same method of finding the median from example B to.
So this median, for example. Okay,
Yeah.
another median you mean?
Yeah, so you
Yes,
find
I will
another
draw it.
median.
Okay, another median, yes. And I don't need the third one, yes, because I know that the third one will automatically pass through this. So that is my center of gravity, and let me call it N here. Okay, then what?
And then, I mean, it shouldn't. You can do the distance from A to G.
Yes.
And then the coordinates for G would be. Oh, but you can't use.
You can.
It isn't the middle point.
No. We had a theorem for that. Do you remember? That was very essential theorem. I told you remember that. So, so first of all, if I want to find the center of gravity, two medians are enough, because we know that there is a theorem guarantees that the third one will also pass through G. So we don't need to consider another one to make it more complicated for us. But of course, there is a theorem. If you don't remember that, then you will be in trouble. So what was that theorem? What was the main property of the center of gravity with respect to the medians on which this is lying? Yes?
H is double the size of G.
Yes, if AG is double size of GN or BG is double size of GN and the other one is the same. Okay, but how should I use that? So don't put the numbers, let us solve it algebraically because I want to have it somewhere for you. Assume that the coordinates are X and Y and Z for each one of them, with indices A, B, and C, and then try to find the formula for X sub G. And then whatever I do for X, I can do exactly the same thing for Y, so let us just do it for X.
A question. If you multiply the length of AM by 2/3,
Yes?
you have the length to AG.
Yes.
And then with that, you can solve out the coordinates, maybe?
Yeah.
Of
It is possible, but I think it is very hard. I think it is in principle it is possible, but you need more equations because how many unknowns are involved for xg? So what you are saying, okay, even if so you said that what should I write? You are telling me that I can write ag is 2/3 of
AM.
am. Okay. And then I don't have any problems with the coordinates of m, I don't have any problems with the coordinates of a, the only problem that I have are with the coordinates of g. But the problem is that if I want to use the distance formula, automatically all the coordinates get involved. Yes? If that was just one equation with one unknown, that was good and reasonable. But then I have to write more or less the same thing for others, or I don't know. You need to find a way to solve that equation, which is not that easy. But it is, we have a better and more simple way to do it here. Okay, I would recommend you, for example, let me just find the midpoint between G to A, and let me call it D, for example. Yes. So what I did, I divide from A to G to two equal pieces. Now how many equal pieces I have? I will have 3 because I knew. Okay. Of course, still I don't know D, so my problem becomes a little bit harder apparently. But then you can solve the problem easily. Why? Because If I want to find x of g, g is the midpoint of d to m. Yes? So I can write that x sub g is equal to what? xd plus xm divided by 2. Am I right? This is xd. Yes? And of course, xm I don't have any problems because m itself is the midpoint of b and c. So what I can write xd plus xb plus xc divided by 2 divided by 2 again. For simplicity, let me multiply everything by 2, so it becomes 2xd plus xb plus xc divided by 4. Yes? But the problem is not solved yet because unfortunately I don't have any problems with x sub b, x sub c because I want to have them, no problems. I'm assuming that they are given, but x of d is the problem here. So what can I do now? D is also in the midpoint of A and G. Is the midpoint of A and G. So xd itself is x of A plus x of G divided by 2. Yes? But I have a factor of 2 before x sub d. So if I ask you what can I write for x sub d, what can I write if I want to continue that? So let me write this line once more. So x sub g is equal to, the denominator is 4. I have xb here plus xc here. Then I have 2xd. Okay, can you help me to write 2xd? Assume now d is the midpoint between a and g. So x of a plus x of g divided by 2 is x of d. So 2 times x of d is x of a plus x of g. Yes? So it becomes x of a plus x of g. But can I say that this is finished? No, because I have x of g on the left and on the right. But it is very easy to make it alone. Yes? I just multiply by 4. It becomes 4xg is equal to xa plus xb plus xc, what? Plus another xg. But I want to find xg, so I move it to the left. It becomes 3xg, yes, is equal to xa plus xb plus xc, and you get a very nice formula. So that's the average of the coordinates, yes? So x sub g that I was looking for is the sum of the x coordinates of the vertices divided by 3. Yeah, so that's a nice formula. So you have the same method for y coordinate, you can have the same method for the z coordinate. So remember this one. If you have the vertices of a triangle, there is a very simple relation that you can immediately find the coordinates of the centroid. Yes? Add the vertices and then divide by 3. So somehow you are averaging among the x coordinates, add them, divide by the number of numbers, and then averaging between the y coordinates and averaging between the z coordinates. Yes? Is that clear? Okay, now I see that it is also good to talk a little bit about reflections and things like that. Okay, so if I'm completely sure that you know that if in 2 dimensions, if I have a point of x and y, if I ask you reflect this point about x-axis, you get a point. Yes? What are the coordinates of this point? Let me call it a prime. What are the coordinates?
X and minus y.
X and minus y. If I do it about the y-axis, I will get minus x and y. And if I do it about the origin, what is the meaning of reflection about origin? It means that you just connect them and then continue it with the same length and you end up with a point. What are the coordinates here? Minus x and minus y. Now let us go to 3 dimensions. I can ask you the same questions in 3 dimensions, but I can also ask you reflection about the planes, the coordinate planes, yes? Let us practice that one. So what will happen if I have the reflection with respect to the, let us consider it z-axis, yes? So this is the z-axis, x-axis, y-axis, and z-axis. If I have a point here and I ask you to reflect it about the z-axis, and the coordinates of this point is x and y and z. What do you think you will get after drawing a perpendicular line and continuing with the same length? What will change and what will not change? Z coordinate will not change, agree? So Z coordinate remains the same, but what will happen to X and Y coordinates? This is the positive direction, this is the positive direction. If you do that, you end up in the negative directions. So X and Y will be flipped to negatives, but the Z will be the same. So if whenever you want to find these reflections, you can just imagine and find them. But now let me just reflect with respect to the origin, like this. I take this point, connect it here, and continue with the same length. What will happen? All of them becomes negative, exactly like the two-dimensional case. Yes? But then what happens if I want to go, if this is the ground surface, I have this point, I want to go below the ground surface by projecting it or finding a reflection. What will happen?
X and Y will stay the same.
Same, Z becomes negative. So imagining these things are very simple. Okay, now if I ask you, of course we can study about this because these are simple, but if I give you just a random plane space and I give you a point and I ask you to find the reflection point, it's not that easy. Yes? It's exactly like the two-dimensional case. If I ask you the reflection of this point with respect to the X and Y axes, you can do that. But if I ask you this question, I have a line, random line, and this I give you the equation of the line, and I give you the coordinates of this point, and I ask you to find the reflected point, the coordinates of the reflected point. So I'm not saying that's hard, but I mean that's harder than the X and Y axis, yes? That would be the same thing in the space. It becomes harder than the two-dimensional case, yes? We will talk if we have time. And if you want to continue with this, we can also talk about those things. Okay, but let me ask you one thing. I give you a point, omega, in a space with coordinates alpha, beta, and gamma. And I give you a point in a space with coordinates x, y, and z. Whatever I'm talking about in 3 dimensions, you can also demote it to 2 dimensions. So now my question is that I want to reflect this point with respect to that point. So it means that I connect it here, and then I continue the line so that the length here and the length here are the same. And then I end up here, and I ask you, what are these numbers? I give you these 3 numbers, and I want you to answer those question marks. I think that's also very simple. How should I do that? Yeah, these are so simple, I don't want to
Shouldn't just be where you plus x divided by 2, but instead, so 2 alpha minus x.
Exactly. So alpha, this omega is the midpoint, yes? So it means that x of a prime plus x of a divided by 2 should be x of omega. But x of omega is alpha, so x of a is given to be x. This becomes x of a prime plus x divided by 2 is alpha, but what I'm looking for x of a prime, so I'll have to make it alone. That's my subject. So x a prime becomes what? I multiply by 2, it becomes 2 alpha, then I move this x to the other side. So it means that I can immediately calculate the coordinates of that point after reflection. Yes? So that's easy. You can do the same thing for the y coordinates, do the same thing with the z coordinates. Yeah. One more thing I want to mention here is about the parallelogram, yes? If I ask you what is the necessary and sufficient condition for 4 points in a space to make a parallelogram for us, in terms of coordinates, of course. So I give you 4 points, A, with XA, YA, ZA, B with coordinates XB, YB, and ZB, and C okay. My question is that, of course, these 4 random points in space might not make a parallelogram for me. Okay, I want, by the way, I want to call it parallelogram ABCD, and the convention is that when you write it in this way, it means A and C are opposite, B and D are opposite. So that's the convention. So it means that you start from somewhere, for example, A, either you have to go clockwise all the way or counterclockwise all the way. So I would write it in, so if I want to name this parallelogram, if I want to name this parallelogram, I'm not allowed to write A, B, C, D. Yes? It's not parallelogram here. I have to write A, for example, B. I have to put C here, D here. Yes? So when I say the parallelogram ABCD, or any quadrilateral, when I name them, by convention, these two are opposite, these two are opposite. Yes? So let us take that one. Can you tell me what should be the condition, the necessary and sufficient condition for these points to make that parallelogram for me? Because if I just take 4 points, there is no guarantee that they make parallelograms. Or you can think in this way. Assume that I give you these numbers, and these numbers, and I ask you to fine-tune these 3 numbers so that when you draw it, it becomes a parallelogram. Yes?
The distance from A to B should be equal.
Yes, but the distance formula is not the efficient one. I'm not against that, but I haven't, by the way, I haven't even checked that because it contains square roots with a lot of calculations. Might be it will work, and in principle it should work, but that is not my first choice for doing algebra. And by the way, let us talk a little bit about that. If it is in 2 dimensions, you have some way to do it using slope. Yes? Because you are saying that if this parallelogram means these 2 are parallel, these 2 are also parallel. Yes? And then you know that for being parallel, the k values should be the same. But one thing, it's good to talk about this now. The k value doesn't make sense at all in the space. Yes? So the slope should be replaced by something more generic. A slope doesn't make sense in the space. Yes? Because we have one more situation for lines. In plane, we do not have this situation. They are not intersecting, but this is not called, this one line is not called parallel to this line. This is called skew parallel. They are not lying on the same plane. Yes. So here, when I am in 2 dimensions, this line, if I consider this alpha, and this line, if I consider this beta, if they are parallel, alpha and beta are the same. Yes. And I don't know. I hope that you know that k value. Another interpretation for k value is the tangent of this angle. Yes, tangent of angle that your line makes with the x-axis is the slope. And why is that? For example, if I want to calculate the slope, you know, I take 2 points, x1 and y1 here, and I take another point, x2 and y2, and then if I want to calculate k is delta y divided by delta x, yes? And then delta y is y2 minus y1, and then divided by x2 minus x1, yes? But let me complete this triangle here for you. This becomes a right angle triangle. If this angle is alpha, I hope that you agree that this angle is also alpha. But this is exactly tangent of alpha, yes? Because tangent of alpha is this distance which is the difference between y coordinates, and divided by the adjacent side, which is the difference of x coordinates. So that is extremely important to realize. This is a better, you know about this up to here. I really recommend you to know that one. So if I ask you what is the k value of a line in 2 dimensions, then you can say the k value is the tangent of the angle that my line makes with the positive direction of the x-axis. If I have a line in this form, then my alpha is this one, and the tangent of such an angle is negative, because the alpha is in the second quadrant, and in the second quadrant tangent is negative, yes? And then you realize that if I have a vertical line, it was not defined, because tangent of 90 degrees is not defined. So that is exactly what we had before. But the notion of slope doesn't make that much sense in 3 dimensions, yes? Because if I give you the angle of my line with the x-axis, it is not enough. Even if I give you the angle of my line with the plane, the line is not clear. Yes, you see, if this is the line in plane, let us assume that I am working in this vertical plane. If I give you this line makes angle alpha with this, then it is clear. These are all those possible lines. Yes, I can go up and down, but I cannot start rotating, because when I rotate, the angle increases. If I rotate in that way, the angle decreases. So if I give you the angle is 30, then you have to respect that the angle should be 30. The only thing that you can do is just going up and down. And if I give you 1 point, then you have a fixed line. Is that understandable? But in a space, this doesn't make sense, because if I give you this line and I tell you that this blue line is supposed to make 30 degrees angle with this, then there are infinitely many of them around. Yes, they make a cone actually. So this doesn't make sense. And even if I give it with the plane, it doesn't make sense. For example, this plane, let me see, this is my hand. This plane, and I tell you that this makes 30 degrees angle here. Do you agree that all of them would also make 30 degrees angle? So fixing the tangent of some angle will not fix the direction or inclination of my line in space. Yes? But the nice point is that the notion of vector makes sense in 3 dimensions again. And that's why vectors are so important. So if I want to, in the future, if I tell you what is the condition for this line to be parallel to this line, even in a space, you can say that this vector should be parallel to that vector. And the reason is that, do you remember I told you that there is no meaning with skew parallel vectors. If I have 2 vectors like that, I can parallel transport it here. So vectors are always lying in the same plane. Well, that's not a big problem. But right now we don't have that machinery to use the idea of being parallel. But I am sure that I think I went on one of these detours in Euclidean geometry. I talked a little bit about the properties of a parallelogram. Yes. So if I have a quadrilateral, so let us talk about diagonals. Let me refresh your memory. What is the main property of the diagonals of a parallelogram? So if I have a quadrilateral, just a random quadrilateral, and if I draw, I don't know, hopefully it can be seen here, yes? I draw these diagonals. And if I draw the diagonals in a parallelogram, there is a big difference between them. Of course, the sizes are different, the sizes are still different. But what is different there and here? So you see here, this one and that one, if you compare them, they are not the same. So this point here, this and that are the same. They intersect. This one and that one are also the same. So it can be shown that, I think it is very simple. I hope that you agree that if I have a parallelogram, this happens. And if this happens, that is also a parallelogram. That is important to realize. Like, it might be a rectangle or it might be a square, but all of them are particular cases of parallelograms, yes? So I would say that a quadrilateral is a parallelogram if and only if the diagonals bisect each other. Yes? I hope, but this is not trivial. It is simple, but you have to work it out. So you need to assume that this is a parallelogram and show that this one is equal to this one is equal to this one, which is very simple. And then take a quadrilateral and assume that the diagonals are bisecting each other, and then prove that that quadrilateral is indeed a parallelogram. And I don't think these are hard. And I think in one of my lessons, in the Detour to Euclidean Geometry, we did that. So let us take this for granted. And now tell me, can I find a relation here? So I would say that ABCD is a parallelogram if and only if IFF. Okay, I want you to fill up the gap. Now that you know the point is the midpoint. Yes, so let me take this one, M. Think in this way. I give you this, I give you this, I give you this, and I demand to determine D in a way that I have a parallelogram. How do you do that? Yes?
Can we use the coordinates of B and B to first calculate M's coordinates? Yes. And then we have A coordinates and M, so we can calculate C with those two. Or can't we do that? Wait.
Yes, the idea is correct, but...
Or
yes.
So
No. I mean, this M is the midpoint of AC on the one hand and BD on the other hand. Okay? So I calculate XM in two different ways. I would say that M is the midpoint of AC. So let me write, if and only if AC, so let me write, if and only if M is the midpoint of AC and BD. So this is if and only if this happens. XM, for example, is equal to XA plus XC divided by 2 on the one hand, and XM should be X of B plus X of D divided by 2 on the other hand, and 1 for X, Y, and 1 for Z. Yes? And then because I am calculating the same quantity in two different ways, they have to match. So this means that this is if and only if that XA plus XB is equal to XB plus XC is equal to XB plus XD. And the same for Y's and the same for Z's. So that is a very good condition to remember. If you have a parallelogram, the sum of the x coordinates of the opposite side of opposite vertices should match. For the same for Y, for the same for Z. Yes? So that is good to know these things. They are actually simple things, but I think it's good to have them. Okay, I think I will stop here, and then next time I want to start vectors analytically, and of course we start with 3 dimensions immediately. We don't need to go to, of course we had it in Math 1C if you remember, but forget about that. What we want to do, we want to start vectors in 3 dimensions analytically. Analytically means that instead of considering vector as a geometrical object like an arrow, we want to consider it as numbers. Yes? And then you will see that we will need 3 numbers in 3 dimensions for a vector. And that is clear because if you have a vector, it gives you, it needs 3 pieces of information. I need to know how many units I have to move along the x direction. I need to know how many units I have to move along the y direction, and the same for z. So then I need 3 numbers. Yes? So then from that point onward, a vector can be viewed in 2 different ways. Either an arrow as a geometrical object, or an ordered triple of numbers. Yes? And then both of them, by the way, will be necessary. So I want to redo all we learned about vectors in this analytic way, and then we can calculate a lot of things exactly, because geometry is powerful, but it is not that strong when it comes to calculation exact values. Yes? So, but algebra is very powerful, so you can find the exact values. So for example, if I want to give you a feeling, of course, if I give you this vector and if I give you this vector, if you want to measure the angle between the vectors, so for example, one way is that if this vector is A, this vector is B, so you can say cosine of theta is A dot B divided by norm of A, norm of B. Yes? But this is useless usually, because if I want to really calculate theta, first of all, for calculating the length of vectors, I have to use measuring tools in geometry, which is not precise. Another point is that what is A dot B? So I need to find a way to calculate A dot B, so that if I put it here, then I can use trigonometry or algebra to find this angle. So now we will see that in the future, this is the definition of the dot product mainly, and then we learn another formula for calculating the dot product. Then if we combine these 2 perspectives, then we will be able, for example, to calculate the angle between 2 vectors. So what you are expecting in the next lesson, I will start it from tomorrow, we will actually review what we learned so far analytically. Yes, that is what we are going to start tomorrow. Thank you. Any questions, by the way?